We're solving problem 15 from the 2019 AMC12B. As shown in the figure, line segment AD is trisected by points B and C so that AB equals BC equals CD equals 2. Three semicircles of radius 1, AEB, BFC, and CGD have their diameters on AD and their tangent to line EG at E, F, and G respectively. A circle of radius 2 has its center on F. The area of the region inside the circle but outside the three semicircles can be expressed in the form A over B times pi minus root C plus D, where A, B, C, and D are positive integers and A and B are relatively prime. What is A plus B plus C plus D? So for this problem, what we can do is we can sort of find smaller portions of the total area. So we have this giant circle, and since F is the center, we know that this upper part is the upper half of the circle. So we can just set that as area A. I know it already says variable A in this problem, but we're not really going to be using it that much. And then these dotted lines that I drew from F extending to these 2 points, well, we know that this entire arc length is 120 degrees because it forms a 30, 60, 90 triangle here. Because this is 1 and that is 2, 30, 60, 90, and then 60 times 2 is 120. So we have that, call all that area the arc B, and then, well, we have the arc. So if we sum this plus the arc, we'd be including this part, this middle semicircle. So we have to subtract that. And what better way to do that is when you subtract this entire top triangle and call that triangle C. So now you just have this lower part and this upper part. All you need to do is to sum these weird looking thingies, the things you get when you inscribe a circle and a square and it's on the corners. So like if you have a circle, So basically what those are is where you have like a square and then inscribe a circle in it. These are the gaps in the corners. It's what it is. So those gaps, there's 2 of them. We call them that D. So it's pretty intuitive to solve for area A. Area A is simply 1/2 pi times 2 squared, which is 2 pi. Area B is an arc, so 120 degrees over 360 degrees, pi times 2 squared is 4 pi over 3. For area C, the big triangle is basically just 2 30, 60, 90 triangles, where we know that the height is 1 because the radius of the semicircles is 1. Then we have, this is 2 times 1/2 times, we have root 3 as the longer length because that is part of the 30, 60, 90 triangle rules times 1, and this simply gets you to root 3. So for area D, the corners, we have 4 times 1, and then you have to subtract 1/4 pi times 2 squared, so, or 4 minus pi. And what you want to do algebraically is you add A, B, subtract C, because we don't want this semicircle, and then add D. So by applying this over here with these values, we have 2 pi plus 4 pi over 3 plus root 3 plus 4 minus pi. So this all gets you to 7 pi over 3. Oh, wait, no, because you subtract this. So you subtract this minus root 3 and then plus 4. So we've now expressed the area of the unshaded region in this form. Then we can add A, B, C, and D. So 7 plus 3 plus 3 plus 4 is 17, and that's our answer for this problem.